Hello, I'm Todd Underwood, and I'm here to present Automating Operations with Machine Learning. This is some work I did alongside my colleague at Google, Stephen Ross. I want to start by acknowledging this is a little bit of a backwards presentation for OpML. OpML generally concerns itself with productionizing or operationalizing machine learning models. This work is more about bringing machine learning techniques to other production engineering or systems operation environments. So let me do a quick intro. This is the agenda. We'll look at use cases and problems, why systems operators want to solve problems with ML. You probably know this, but we'll cover it. What primary candidate types of applications exist in this context and why those don't work as well in practice as we would like. Many of them have good research results, but the results do not turn out to be as strong in practice. We'll go into a few of those techniques in some detail and try to understand where they break down or where the gaps are in terms of bringing them practically into use. And we'll find, spoiler alert, one technique that works pretty well and people should be using more. And finally, some recommendations for future work. So some basic questions phrased as fundamental philosophy problems, because I don't think that OpML has quite enough philosophy in the content. So the identity question, who are we? So Stephen and I have both been at Google for coming on or a little bit over 10 years. Both of us do machine learning work. Stephen is the tech lead for ML Infra SRE, which is the portion of ML SRE that does internal work for internal Google users. And I lead ML SRE as a whole, so that includes the cloud stuff. Other minds question, always of doubt, who are you? Even more true now as I'm just speaking to a camera and none of you are there, but I hypothesize that you do exist and that you will see this video somewhere. In case you're not sure who you are, I probably cannot help with that, but here's who we think you are. We think you can spell ML, which is good, and you might know a little bit more about it. In fact, you probably know more about it than I do. We think you're somewhat interested in the challenges of production engineering. You may have focused about the challenges of production engineering in a systems environment for your machine learning models and applications, but now we're asking you to think a little bit more generally about bringing those machine learning techniques to production engineering as a whole. Teleology, why are we here? There is a persistent, widespread desire to bring machine learning to all the things. And in the context of large-scale systems design, large-scale systems architectures, it's to bring machine learning to automate operations of those. Operations are the activities necessary to maintain the functioning of some computer system. That's what we're talking about when we say that. I think there's the myth that we can just sprinkle the ML sprinkles on top of production engineering environments and make them better. But in practice, very few of those applications work very well compared to the cost of implementing them right now. And so we want to sort of do a little bit of myth busting on what seems to be easy but isn't, and then investigate which parts of this actually do work. Epistemology, what do we know? Well, we know a lot of what doesn't work and roughly why it doesn't work. We know a little bit less about what does work, and we have some ideas on what we should all try next. Reminder, and this is probably obvious so far, both because of my organizational affiliation and also because of the content of the talk, but we're talking about large-scale computer systems offering shared services of some kind. So we're talking about data center environments, lots of computers doing something for some set of applications for some set of users. Not necessarily on the internet. They can be, privately managed, but that's the context that we're talking about. Production is the environment with the highest availability and reliability requirements. And so many of these observations may apply to other environments, healthcare, manufacturing. We didn't make any effort to do that application at all. So it's beyond the scope of this presentation. If they do apply, please let us know. We'll happily refer people to your work showing whether our findings apply in those environments. So let's talk about use cases and problems. So what is it that systems operators want to do with machine learning? Well, they want to automate annoying, repetitive, boring tasks. Now, typically, those annoying, repetitive, boring tasks are either done by hand, in which case they're annoying, repetitive, and boring, or they're done using some sort of heuristic, some sort of threshold, some sort of pattern matching. And so the problem is that those heuristics may be brittle and they may not be very accurate. So for example, the kinds of things people would like to automate are anomaly detection, look through my logs and tell me if anything strange is happening. That's a thing humans can do relatively well and computers are terrible at, and heuristics really struggle with anomaly detection. So many things that only happen once are not anomalies. They're actually an expected result. Automated monitoring maintenance. So I have monitoring and things, I have thresholds, but now things have grown bigger, and so my thresholds are not accurate, and I need to update those thresholds. Capacity planning and prediction, and maybe capacity fulfillment. How much network resource of some kind am I going to need to meet my customers' needs in the fall, in the spring, in 2022? Right now, that's a process that's relatively manual. Again, human beings are relatively good at doing that analysis, but it's very time consuming. And then automated service and resource scaling, certainly related to the last point, but where do my services on a much shorter time scale, like right now or next minute or next half hour, need more or fewer resources? So what goes wrong? Well, the punchline is there's generally not enough labeled data, and the machine learning solutions that are deployed are generally not cost competitive with simpler heuristic solutions. So getting a large amount of high quality labeled data is actually very difficult. The labels are difficult to automatically apply. So semi-supervised approaches struggle because the problems are dynamic, making the appropriate behavior look anomalous under some circumstances, since it's new, even though that might be the new state of the system. Reinforcement learning requires some clear rules, and in many of these systems, clear rules are actually difficult to produce. And getting more higher quality labeled data is going to be expensive. Some of the problems are only amenable to some very expensive machine learning approaches, and heuristics can often get comparable results with much less effort and much lower cost. So if you have a heuristic solution that's more or less as good, but costs you 1% as much time, as many machine resources, you may choose to simply use that. So let's look at what kind of works in the research and how and whether it fails in practice. So here's how we evaluated ideas for machine learning. We looked through a bunch of use cases. We looked for evidence of ideas that had been demonstrated in a reasonable production use case, so scale, complexity that emulates what somebody might see in a real environment. Is there enough data available to significantly beat heuristics? Is there a practical way of labeling those data? How expensive is it likely to be to implement? And how reliable is it likely to be? And reliability is, in this case, mostly about model accuracy over time. So does the model accuracy change over time? Where we looked, well, so obviously we looked at our colleagues' projects, who our colleagues are always proposing silly things, just as we are always proposing silly things. And so we looked for Google projects that have either been proposed, evaluated, or attempted to be implemented. We did a broad but shallow literature review for implementations of most of the techniques mentioned above. Let me make sure to highlight, most of the cited research is not Google work. There is one paper that had was from Google, but most of the research is from other people. We're really grateful for the excellent work of so many teams trying to tackle this question. So let's look at the first idea. So the first idea is anomaly detection from logs. Generally, look through the logs of some system where it's reporting things that happened and identify when something went wrong and schedule that for human review. Seems like a reasonable idea. Looking through logs is a painful activity that almost no one wants to do. Our evaluation of this is still an open research project or open research topic. So, and let me explain why. So here are some of the problems, and many of the problems in these cases will be repeated, so pay attention to the qualifications or the categories of them. So cost. Large log files require expensive processing. So the larger your log files, the more expensive to go through all of your log files. And of course, if you have small log files, then you can go through them in a simpler way by hand. So there's a cost-benefit balance here on how much you're logging and how much logging you're processing. In addition, ordering, many of us have systems that have more than one computer doing the same thing at the same time. And so ordering those logs can be expensive and challenging. Fragmentation, so the full state of any given log might be spread over time. So for example, you could have a system where part of a transaction on one application, and then that state is passed to another application, and that completes the transaction. It's difficult to replicate the full transaction state across that transition. Consistency, people change logging formats, and we have to track those changes over time, and that complicates doing machine learning and doing the evaluation automatically. And dynamic, not just the log formats and outputs, but also the human behavior changes over time. So if all of a sudden everybody is buying Candy Crush tokens today and nobody's buying Candy Crush tokens tomorrow, does Candy Crush have tokens? I realize I've never played Candy Crush. Sorry about that, but it was just an example that occurred to me. If that's the case, then like, is it anomalous that all of a sudden the rate of Candy Crush token purchasing declined? No, in fact, it's correct. It is, business-wise anomalous, but it is not an anomaly that you would flag for systems integrity or otherwise availability of the system. Labeling logs as anonymous is generally a hard problem. So usually you need an expert to label them as anomalous at least the first few times. And there may be a very limited number of true positives that you need labeled in order to identify future true positives. And by virtue of definition, anomalies are anomalous. So there's a poor signal to noise ratio for logs. Many anomalies are fine. This makes labeling them hard. Ideas for how to mitigate some of these. Certainly you can mitigate the consistency and cost with some major engineering investment to invest in machine learning optimized logs. So you can either pre-process all of your logs to make them easy to train on in a very standard format, or you can populate a sort of standard formatting throughout your log stack. So that can help with the consistency and cost elements. The rest of these are actually still probably pretty challenging to address. Let's look at the next topic, alert triage. So here's another idea that we found that is relatively common. Given a set of alerts, determine which ones do not merit human review. So I have an alerting system. It has some rules. The alerting system is there in order to draw human attention to things that are going bad right now. As any of you who has ever written such a system or been subject to such a system, there are false positives. Your choices are false positives and false negatives. And depending on the value of the system that you're deploying, you may choose to tune it to have quite a few false positives so that you don't miss outages in the system. That can be expensive, and so you'd like to filter these. So what are some of the problems? So we've got the consistency and the dynamic problems similar to logs. So consistency alerts can be formatted in lots of different ways. And unless you rigorously standardize that, it becomes very difficult to process them into standard features in an ML system. Those alert frequencies can be quite dynamic and shift over time based on the changes and the functioning of the system and the changes of the use of the system. So any given model needs, to adjust to that. In the results that we found here, the effectiveness, the most effective results we found only eliminated 2/3 of false positives with a minimal loss of true positives. So I want to be careful about how I characterize that. That's actually an impressive result. Eliminating 2/3 of the noise is eliminating 2/3 of the noise. On the other hand, as you look at how to tune such a system, what you may find is that that's just not enough, that 1/3 of the noise is still quite a lot of noise. And the expense of doing this whole system and maintaining this whole system may be outweighed by the value of it. And then, of course, labeling. So the biggest problem is labeling. Labeling requires skill to label an alert as anomalous or not, or meritorious of human intervention or not. And in a stable system, you may have a limited number of true positives. And so there really may be limits on the number of labels that you have. So ways you can mitigate. Standardizing alert format is a good idea for a bunch of different reasons. So if you are considering this kind of application, you should do that. You can possibly get manually label enough true positive alerts that you can use those alerts to train on other aspects of the system. So it is possible that you can have a manual effort of labeling. And then finally, you can absolutely periodically refresh a model. So that will address some of the dynamic concerns of changes in the use of the system, et cetera. Let's look at the next idea, security. So I'll just say from the outset, security is a big topic. The point here is not security in general. The particular piece that we looked at was studying advertising security, and in particular, detecting adversarial advertisements in the wild. So this was an ad placement system, and at Google, we do some ads. You may have heard about that. And so one of the things that we need to do is identify malicious ads and do that, if we can, accurately and automatically. So we want to detect malware, intrusion, and insider attacks that standard heuristics can't catch by flagging binaries, apps, devices, and flows and users. So that's the general idea. The specific application we looked at was adversarial advertisements. So what are the problems? The complexity of this space is enormous. So you really have to narrow down the scope of application that you're interested in evaluating. And so this is quite difficult. Dynamic attack types change rapidly, sometimes over the course of hours. So a new attack appears. It is exploited for as much time as they think you can tolerate. And then it is they move on to another attack. So this is a very dynamic system, not changing over the course of days or weeks, but in hours and in some cases minutes. You need enough data. So you will need enough real incidents, like actual incidents of a kind of attack, in order to provide training for a model. The challenge is many people don't have enough attacks. I know that might not seem like a challenge, but without enough attacks, you won't be able to recognize new attacks. So if you're fortunate enough to not be attacked very much, you may not be able to train a system that works relatively well. And again, our old friend labeling. Labeling an attack usually requires an expert. So with a limited number of true positives of any given type, many possible combinations of variables to train over, it may, without sort of just generating a huge volume of alerts that are candidates for labeling of an attack, it may be very difficult to use human labeling to get a training set here. Mitigations, well, we can build tools for domain experts to search for, find, and analyze incidents. So this is basically, you can build an automation framework to help with the labeling problem. And you can find those rare true positives. It is expensive to build such a framework. You need, a searching and filtering process, and you need a set of automation tools and reasonably good UI to be able to present to experts. And then you need those experts to sit down at a screen and really go through a bunch of things and label them. Once you find a few true positives, you can use active learning to build a model, gradually finding more of them. You'll have to periodically refresh the model with new data very frequently, including periodically refreshing the labels as new attacks become common. So this is possible, and the result from Scully et al. Shows that this can be done, but it is difficult to do in practice for most people for these reasons. Let's look at the next one, autoscaling. This is by far the most successful of the applications that we looked at. So what is the general idea? We want to use historical usage patterns compared to the current usage to estimate future resource needs and to scale capacity up and down to meet service level objectives while saving money. So you think of, and by historical can be last hour, last day, or last year. We don't really want to scope what the degree of hysteresis of the system is. We only want to say, look at the past, look at the present, predict the future. It turns out this works relatively well. So here are some of the problems that have been solved in these applications, and there's a link to one of the more detailed studies of using machine learning for black box autoscaling. So it is an effective solution. So substantial amounts of demand do have predictable cycles. So there are diurnal cycles of when people are awake and when people are asleep in different parts of the day. People have predictable levels of engagement with different kinds of applications. You might want to check your email or Slack first thing in the morning, but maybe not an hour and a half after you've started work, etc. You watch more TV and more YouTube and more Netflix in the evening than you do in the morning. And so there are predictable patterns, and ML can definitely beat heuristics by taking advantage of these and identifying predictive patterns. Additionally, that's dynamic. Periodic retraining can adjust for pattern changes. The data can be automatically labeled. So we know when we're running out of capacity or have run out of capacity, and we can get some exogenous signals for that. And the cost benefit here is this can pay for itself very easily by saving of resources. There's one challenge, unforeseen demand spikes, if they exceed the responsiveness of the system, will still happen. And so you will still either have to set aside spare time or spare capacity, or you will have to tolerate short-term outages as the system scales up. So here are the key results. Many problems are dynamic, and so you have to refresh models. Human labeling is expensive compared to the value that it provides for most applications. I think many people knew that, but let me just say again, human labeling is expensive. Humans are tricky, expensive beasts. While many ML techniques do solve operational management problems, they do so, and they do. There are really good results in these papers, and I encourage people to look at some of them. They often do so at a cost that is higher than the value they provide. And when we think about cost, we think about the machine cost of the system, the human cost of building and maintaining the models, but also the cost of maintaining the overall complexity of the model architecture. So if you need to standardize and pre-process all of your logs data, that's a whole extra system you have to build and maintain. So you'd better be getting an enormous amount of value out of that, or it just simply isn't worth it. One common alternative, straightforward heuristics, is very popular. These are brittle. They're much less flexible, but they're almost as good as machine learning applications, almost as good as machine learning for many applications, and they do so at a fraction of the cost. So of the techniques we evaluated, autoscaling was by far the most effective application of ML. So future work. This is the section where we either say what we're going to do or we tell you what you should do. So frequently what I say in these sections is we should really all get our data together, because if our data were carefully organized, this would all be easier, and many of these applications would have worked well. So we think that as we looked at what we intended to do in past presentations and past work that we've done, what we had planned to do was we were going to enumerate our problems. We were going to curate and collect the data in a very standardized, very simple way. So it was ready to be machine learned, all, whatever application ideas we came up with. And then we were going to use those data that we had collected and standardized to build models and solve problems more easily. Seems good, right? This was our plan. What we actually did was we didn't do most of that. Since the last time I've talked in public about how some of these ideas don't work that well, we didn't do basically any of that. We did procrastinate. We did some hoping. We did a little bit of complaining. Actually, we did a fair bit of complaining. But it turns out that difficult to justify big projects with far off benefits are difficult to justify. And so it's very difficult to explain why 5 people are working on collating, standardizing a data stack for no particular application, when you know that the particular application you have for that stack is not feasible given the state of maturity of the data stack. So maybe here's what we should actually do. This is what we're thinking now. We need to identify a few simple technologies that work and start getting value out of those. Build small, modest, short-term projects that have deliverables that are actually, apparent within short periods of time, and use that to try to build more momentum for more successful and more impactful operational approaches and machine learning approaches to operations. And so we're going to try that. We'll see if we have a little bit more success on some of those techniques, and we will report back in the future. So thank you very much. I leave you with I can't tell if that's a happy kitty or an angry kitty, but that's the cat that I will leave you with. Appreciate all of your attention.